Hi, Eddie.
Hey, hey,
Hey,
Andy.
Eddie. So, so here we are. Should we give it a few minutes for people if anybody else joins?
Right now, just two of us.
Uh-huh. Yeah.
Oh, yeah, of course, we need to.
So we're recording. And, yeah, let's give it the
Recording is going.
traditional run out until 5 past, sorry.
I'll go on mute as I was a little bit hectic morning. Need to get some coffee and something else too. All right, I'll
Yeah,
be back in a minute.
whatever you need. Yeah, that's great. Cheers.
Hello, Andy. Hello,
Hey, RT.
hi, Andy and Eddie.
Hey, RT, sorry I'm muted. I need a minute. I'll be back.
Yeah,
Yeah,
we're gonna.
how are you?
Yeah, pretty good, RT. How are you doing?
So far so good.
So far, so good. Yeah. Okay. All right. And I see we have Russ joining us too. That's great. Hi, Russ. We just, hey, Russ.
Hey.
We're just giving it until 5 past the hour in case anybody else joins. Then we'll get into it. Eddie's just getting, I think he's just getting a coffee. So give it one more minute or so. Mhm.
Andy, do you plan to speak at the EMEA summit at Barcelona?
Yeah, yes, I do.
Okay,
We submitted a breakout session based around the work in this work stream. Uh,
okay, great.
and we'll see if it's accepted. Yeah.
Okay, great. Yeah,
If not, then um, if it's not accepted, then we'll be able to give an update via um, the solutions committee updates as we have done as we did at the global summit, I think. So yeah,
okay, yeah,
yeah. See, we've got a lot of. There's been quite a lot of developments in the tool made. So which I want to kind of share some of that with you guys today in this session as we're working
great.
towards. Um,
Yeah, it's being recorded. Let's
yeah,
get started. Let's go over the updates
okay,
and maybe we'll
yeah,
go one more time through the flow of
yeah.
the.
Let me just give me a moment. I'm just getting some visualizations of the updates ready. Just give me a couple, 20 seconds.
Good time.
And I'll share my screen and we can get started. I want to show you guys a before and after, basically, of the structure of the data center as we have it in the model. There we go. That one. Oh. Me. Okay, share my screen. Yep. Okay, so welcome everybody from myself and from Eddie. Let me know when you can see my screen, and I'll talk to the.
Yeah, it's visible.
Super. Okay, so let's do this visually. So we have the current model basically represents the data center in this way. So basically from the outside in, we have the overall data center facility that breaks down into power systems, cooling systems, and data room. The data room itself is like a cascade of equipment. So the data rooms, well, we have 4 data rooms defined independently, themselves made up of 4 clusters, and the clusters are made of racks, and the racks contain chassis. So that's the overall structure. What you will have possibly noticed is that the cooling equipment is placed at different levels of that structure. And we needed to make some updates to the tool because the cooling equipment is getting integrated closer to the IT equipment. So where previously the cooling distribution unit and the perimeter cooling or the fan wall or CRAM or generally were placed more at the data room scale. These now, due to the architecture of the cooling infrastructure, are now placed closer, deeper in the structure. So not at the data room scale, not necessarily perimeter cooling or CDU to service a whole bunch of clusters as shown here. They're now more brought into the cluster level and indeed into the sort of rack as well in some cases. So you can hopefully, if I zoom out, you can see, so V1.1 is what we have released already, based on that kind of disintegrated situation where the cooling is on the data room scale. So we've been working hard to integrate the cooling, these red blocks, as you can see it, now closer to the IT, deeper in the structure, adding more options, enabling the model to handle a fuller range of configurations of cooling systems because to reflect the range of liquid and air cooling options and combinations. So now we have, so we've kept the air cooling at the data room scale because that still exists. Fan walls and perimeter cooling is still existing, but this is now in combination with air cooling at the cluster level and air cooling at the rack level. And I'll talk about what types of physical equipment can be applied in those locations. But also, and more importantly, the liquid cooling, which was a CDU at the data room level, is now placed at the cluster level. We also have a block for a distinction between facility water, low and high temperature cooling, but also technology water cooling equipment at the rack level. So this enables us to more fully and transparently represent the efficiencies of power and cost of those objects in the stack of equipment.
Andy, I would just quick question. I would assume that in the cluster, you can specify how many racks per CDU, correct?
Yeah, exactly. So, well, so you specify, so yeah, you can specify the number of CDUs in the cluster, and as well as specifying the number of racks.
Number of racks, right? You can get there. Okay, okay.
Yeah.
And where L1 now? L1 is still data room, right? Or is it full facility?
Yeah. So L1.
Oh, full facility. Okay, okay.
Yeah, basically the critical power out of the UPS.
Yeah.
That enters the data room. So those locations are still aligned with as they are defined by the Uptime Institute for the PUE calculation. Okay. All right. So so what that means then is that we can let me just show you. So you can basically configure equipment or configure that the tool can be configured to represent a great range of combinations for cooling approaches or approaches to cooling in a data center. So it can handle obviously still the very basic situation where all of the heat from the goes to a CRA and then is cooled via the low temperature heat rejection unit. But you can also add, but then you can build out to very complicated configurations. For example, where you have direct chip cooling in the chassis, which is cooled to the high temperature heat rejection unit, and then the remaining heat on the air side is cooled by a Viridor heat exchanger that itself is liquid cooled by the low temperature heat rejection unit, with the remaining heat loss on the air side in the data room being soaked up by a CRA in the perimeter. So it covers the full range of combinations, which is really important, I think, because as we've said before, there's the number of options and permutations at different scales of the data equipment structure of data room, cluster, rack, and chassis. You know, the tool's scope is to deal with those all of those different options, and those options are broadening as innovations in cooling is happening. So this is, so are there any other questions on this change before I show some examples of how it's implemented and used?
Do we still have L4 or is it obsolete now?
Still have all sorry, Eddie, can you say again?
I'm sorry, do we still have level L4 or is it obsolete now?
L4 is, I'm just not showing it because it didn't change, but it's the same. So the chassis level equipment is unchanged.
Chassis level. Yeah. Okay, got it.
Well, L4 is kind of like our own kind of, it's basically like a server PUE. And yeah, that's still represented to capture the cooling overhead within the chassis itself, like the chassis fans, for example.
Got it. I just saw L3, L4 in the upper diagram and I couldn't find it on the lower one. So
fair
got
enough.
it.
Yeah.
Okay.
Fair enough. I've been a bit challenged on time this week, but you know, we're making good progress here, so it's all good.
It's good.
Okay. So you're probably wondering then, so that's the why we've made this change, to make the tool more flexible and accommodating of approaches for cooling that exist in the industry. So how does this work? How does this look? What does it change about the workflow in the tool? So all of these changes are at the data level. Let me just collapse a bit of this. Okay, so the tool is unchanged in some senses, that the high level information that is used to represent the data room is unchanged. So if you look at, and the structure in the data tab of the tool, the high level information of the rack, of the configurator for rack cluster data room is largely the same, and the library of equipment is largely the same. So maybe if we dive into this, so the rack configurator, so this is post the changes. So now we have in the rack, we can now configure options for air side and liquid side cooling. Maybe what I should do, Eddie, is bring the diagram alongside so you guys can see a visualization of it alongside the spreadsheet. So here you can specify what equipment is sitting in this place. And I've done some pre-configurations of different rack level cooling options. So we have sort of basic air cooled as the default, as you might expect, where all the air in the chassis is just, there's no special equipment in the rack. The chassis just pushes air into the cluster directly. So that's the most basic configuration. And then next up is where we place a rear door heat exchanger in the on the air side. Of course, the rear door heat exchanger absorbs the air side heat rejection from the chassis, but then the rear door heat exchanger itself is cooled by chilled water. So that, and then in the most case, the heat is then rejected to a low temperature chilled water supply. So that's represented in this configuration, and we can dive into the details of that. We also have a direct-to-chip sidecar, basically where you have a rack sitting alongside the IT rack. In that case, the sidecar is so the heat's rejected from the chassis two ways, a proportion on the liquid side, sorry, over here, which is then cooled by the sidecar, which would be sitting in the TCS location. And some of the heat is rejected to the air side, which is going in that case to the air. Of course, the majority, the heat is absorbed in the sidecar onto the air side, so it diverts the rejected heat from the sidecar into the cluster air heat rejection stream. So all the heat from the sidecar goes to air, as you can see. So it's comparable in terms of its heat rejection pathway to a standard rack. But the and it will have a higher power consumption because, of course, you've got a larger set of fans on the sidecar to drive through the necessary flow resistances to the air circulation. So,
India, I'm sorry for interrupting. And guys, my apologies. I have some situation I need to attend to it. It's non-work related. So, if you don't mind, just
yeah,
going
sure,
through
we'll
the
keep
call,
going.
and I'll be back. I'll check
Okay.
with you later, Andy. Thank you.
Okay.
Sorry, guys. Yep.
Yeah. So yeah. So sidecar is implemented. CDU, and then this one shows the combinations thereof. So you can have a CDU to handle the liquid side heat rejection, and then a rear door heat exchanger to handle the air side heat rejection. So in this case, you can see that there is, yeah. So that accounts for the combination of the overhead power for the CDU and the rear door heat exchanger. It accounts for the capital cost of all that extra equipment, the floor area, and but as you would expect, the the heat is rejected to majority to the TCS heat rejection pathway. The remainder of the heat, the majority, is rejected to the low temperature chilled water circuit via the Vidor heat exchanger, with some ambient losses, just to illustrate that functionality in the tool, where you can basically have a four-way heat rejection pathway according to the equipment that you select. Are there any questions on this functionality and these sorts of configurations? Are there any configurations that you guys think we need to add that you know exist in data centers for liquid cooling?
Andy, I think TCS is combined with FWS, right? But air has nothing to do with FWS, right?
Yeah, TCS is basically, so this is the rack level.
Yeah.
So the rack rejects heat for liquid cooling via the TCS, and then that's picked up by the CDU, which is at the cluster level.
Yeah.
So if you look at what type of equipment is configurable at the rack level for liquid, we have options of none, i.e. where all the heat's rejected on the air side, a sidecar where there is, so that is a form of CDU, but it's associated directly with the rack, hence it's defined at the rack level. So a sidecar is matched to a specific rack. So TCU, so in that case, if you like liquid to air cold plate cooling via a sidecar is defined at the rack level. As you can see in this case, so there is no heat rejection, as you said, to TCS, all of the heat is essentially rejected to the air side and received by whatever cooling there is at the chassis level. At the cluster level. But for
okay.
Yeah, but for conventional CDU cooling, so where there's directed chip that's cooled by conventional CDU, it rejects it via TCS because that's picked up then by the CDU, which is defined at the next level up, as you can see here, at the cluster level. Yeah, does that answer your question? And do you agree with that configuration?
Yeah, but user need to input they need to input independently
the way the tool works is that basically you configure a rack.
Okay.
And then once you've captured the resource
So they
efficiency,
must have basic cooling knowledge to use it to make it relevant, right? For example, if they choose sidecar or they choose crack, they cannot they cannot input value greater than 0% to TCS, right? Something like that. So they need to have basic knowledge to use the tool correctly, right?
well, the user can go as deep as they want, but they can also go as high as they want on this. So we pre-configure, as I'm showing here, typical configurations for different technology sets. So if they know that they want to compare direct-to-chip to rear door heat,
Yeah.
then they have it. And so you can take a pre-configuration of a Vidor heat exchanger rack And then when you get to the, which I'll show you next, when you get to the cluster scale, you can then build a cluster from those racks. Yeah.
Yeah, right.
And then once they get, but if they want to go deeper,
Yeah.
they can get into configuring a rack at this level, but they don't have to, right? So that's I think that's the point that answers your question, because the tool has pre-configurations of IT equipment at every level. You can just operate at the at the highest level, which would be the input level. So you can still configure your facility by selecting data room types. Yeah.
Yeah.
As you
I
can
see.
see here, yeah. So data rooms solely based, I mean, this is for like a homogeneous example where everything in the data room is cooled by a VLO heat exchanger or direct chip or so on in its different forms. So you can accept the pre-configuration at a level up to as high as the data room or as low as a rack level, and use that to compare and contrast. If you don't find what you and the goal here is to build a tool that has got the flexibility to accommodate all of the options available in the industry for liquid cooling, which I believe we have now achieved, with the equipment placed at the right locations to reflect the energy architecture for heat rejection. But of course, having the tool open enough so that when a user would like to get into the details and dig deeper, that we have a consistent approach to the configuration at every level. So we're showing you here the rack level configuration tool, but if you go to the next level down, which would be the cluster configuration tool, it's the same workflow. So in this case, you can see that you can select a pre-configured rack, the one that we've just been talking about, or the list. So here's the same list of racks that we were just talking about at the rack level, available at the cluster level. So you can go ahead and choose one from the
This is
or choose the one that you just configured yourself.
this is pretty flexible. I know, but if they don't have sufficient or relevant knowledge where they configure an irrelevant combination.
Are you saying that the tool needs to ensure that the configurations are
or give some restrictions? Yeah. Otherwise, they may configure an irrelevant combination, right? Something
Yeah.
like yeah.
So what the tool does is when you make a configuration, it will give you a summary of margins for power and cooling. And so if you it's possible that you can configure equipment with insufficient power supply, where the critical power supply isn't sufficient to power the racks and say the CDU, which is all on the critical power pathway. So it will tell you if you've exceeded, it will tell you how much margin, how much excess power availability you have.
Okay.
It doesn't stop you from doing it, but it will, here is where it will give you a warning, both for the capacity of the power, but also the capacity of the cooling. So in visual terms, the tool will give you a warning here if the PDU isn't sufficient to power the racks and the CDU, for example, and in turn, if the CDU isn't sufficient cooling capacity to cool the heat rejected the liquid side from the racks.
Yeah.
All right. So it does have some. There is some warnings, I suppose. So the process would be that you would make a configuration. For example, we can pick, for example, if we were to pick, say, well, we'll just use actually, let me see. Let me see what we can do. So yeah, basically when you're configuring, when you're choosing the number of PDUs or the number of air cooling equipment or CDUs that you have, if these numbers are not high enough, then you're going to have a negative margin here, and you'd have to increase the number of, or select one with a higher capacity. Yeah. So that's the workflow. So once you make a configuration, you check your margins are good. Here's the characterization of that configuration. And once your margins are good and you're sure it's what you want, you then copy it into the table to make it available for the next level up in the data architecture.
So is there a precondition that the bottleneck is on the TCS side, or both FWS and TCS sides are variable?
Yeah, so this is the TCS. So let's talk about this. So we're at the cluster level here. So basically it's saying all the heat that's received by the CDU via TCS has to be within the capacity of the CDU type and number that you've configured.
Right.
So that's what that box does. This box here does on whatever equipment you may have configured on for the cluster level side heat rejection. Yeah. And then, of course, the top box is for the critical power supplied to that cluster. So, yeah. So for where you're making choices for capacity of equipment, which at the cluster level is basically is on the boundaries of the cluster, yeah, where the interfaces are to the larger power and cooling infrastructure. So the PDU, the cluster air handling, and the CDU, those three interfaces to the external heat rejection is where the margin feedback is placed. It doesn't check whether there's capacity for the non-critical power, because that equipment is driven by the demand, yeah, rather than sized according to the cluster configuration. And the same goes for the heat rejection unit. That's the sizing of that is driven by the demand. Does that, well, hopefully that helps RT to answer your questions. Are there any other questions, RT, or anybody else want to ask a question at this point?
Yeah.
Okay. So yeah. So that way of working is present in all of the levels of the IT equipment. What I'm working on right now is to bring this into the model, just reintegrating the changes. So just at the overall model level, we're also making some updates. So previously we made it, well, previously the power capacity of the IT equipment was set in the configuration, and you could then choose the number of data rooms of a particular type that you had, and how many clusters of a particular type that data room contained, and so on. And that kind of preset, that the configuration of the IT equipment preset the capacity of the data center. We've changed that so you can scale the data equipment to achieve a target data center power capacity. And previously that was done at in the facility level, but we've broken down that so you're able to dial in a power capacity per data room to give more flexibility in the tool. So for example, in this case that I'm showing here, well, in general, you have the ability to select a data room type for 4 different data rooms, right? Just like before. But now you can then, for each of the data rooms, you can dial in a number of kilowatts or megawatts for that data room, defined at a certain location in the critical power pathway. So in this case, I'm saying I have one data room. It's a type default. That data room is 10 megawatts, and that 10 megawatt set point is made at the output from the rack PDUs. So that would be at this location. So that you can then go ahead and add an alternate type of room. In this case, it will be based on a different type of cooling approach. And you can dial in a certain amount of kilowatts at that same location, at that L3 location. So you can mix and match data rooms, and you can scale up and down the capacity of that data room at a preset location consistently across your infrastructure design. Which gives you, again, it's about giving you it's ensuring that the tool has flexibility, but also clarity on what you're comparing each of the scenarios to. So in this case, you can configure it so that you're comparing that you have like a legacy data room, which might be default air cooled, 10 megawatts each, and then you're comparing how does my TCO look like if I add 5 kilowatts via a read or heat exchanger approach or a direct-to-chip sidecar approach, and it will then use the pre-configured data rooms to and calculate all of the OPEX and CAPEX implications of those choices. Okay, so that's where. So this is the highest level of configuration RT, where you don't need to know a lot about what's inside the data room equipment, or the cluster, or the rack, or even the chassis level equipment. You just know the name of what you're looking for. Yeah. Of course, if you want to, and then you can go. So this is the top-up approach, which is driven by the main input screen, and there is a far richer range of data room types, and a far richer range of liquid cooling approaches possible in the tool, which is really helps to enable the industry to compare and contrast different cooling technologies, and indeed power and technologies as well. Okay.
Yeah.
Any questions
Okay.
on that?
And for the heat rejection unit, currently we have dry cooler only.
Let's have a look. So for the heat rejection unit,
Yeah.
we have the ability to operate the heat rejection unit. It's probably easiest if I show you this as a picture, RT. Well, I always find it easier with the picture. But basically, here's our heat rejection unit here on the right, if you can see that. So our heat rejection unit receives heat from the data rooms. It then can be operated in two modes, either a free cooler, which can be dry or adiabatic, or it can be operated in an active mode where the compressor is running and the model calculates performance of the data center in both free cooling and active modes where the compressor is running, and scales the OPEX according to the economization hours, which is dependent on the geographic location and associated air temperatures. So in answer to your question, yes, it has a dry cooler, but it also has other forms of economized heat rejection. But it also has an compressor-based heat rejection.
Yeah, I see.
And it selects those according to the prevalent conditions, dependent on location.
Yeah, I see. Mechanical cooling and free cooling. But my question is there an option of evaporative cooling?
Of course, yeah. So what that means is that you just have a different resource efficiency on the free cooler side.
Okay.
So you're running fans in all cases, of course. You're running a pump in all cases, of course. But the free cooler, you can add. It can be just a dry cooler here, or you can add adiabatic. And so when we come to heat rejection, this is where you can define the
Okay.
the water consumption. Yeah, here we go.
Okay.
Yeah,
I
so
see.
on the fan block, which is the ultimate heat rejection to the ambient air, this is where we define the water consumption rates.
Okay.
It can be either a fixed rate, a volumetric consumption rate, or it can be associated with the load, the heat load on the heat rejection system.
Oh, great. Yeah. Okay,
Yeah.
no problem. Yeah.
Yeah, and of course, in that case, for adiabatic, if you wanted to reflect a change to the load on the fans, or effectively the load on the mechanical system for adiabatic, where you've also got a pump to overcome the back pressure of the spray nozzles, you could bundle a lower COP, here, or set a lower COP here to reflect the fact that you've got fans and evaporative water circulation pump. Okay. All
Okay.
right.
Okay, no problem. Yeah.
Yeah. So so it's not perfect, but it's comprehensive. I think imperfections really come from, as we discussed many times before, the fact that the efficiencies are fixed point. They don't reflect, they're not dependent on, well, the efficiencies are fixed. Well, you can have a fixed or proportional, but they're linear. They can't be made a complex function or dependent on the load, which is one of the limitations. But I think we've taken it as far as we can within Excel, bearing in mind the lack of access to macros to do the more computationally expensive step of nonlinearity. Okay, so the work in progress right now is just to build the changes to the data equipment scope into the user interface for input and output. Input is done. I've shown that here today. And we're just sort of hooking up these changes to and doing some checking of the calculations to ensure that everything is good. Once that's done, we'll then update the documentation user guide, and I'll write some notes on some technical notes on the technical approach taken to give those interested users insight to how we've implemented the calculations. And then that's pretty much a wrap for this version. You know, we would greatly appreciate any feedback, and I really appreciate the feedback, particularly RT. You've asked some very insightful questions, which are very thought-provoking.
Yeah, so this version hasn't been released, right?
No, this is work in progress.
Oh, okay, yeah.
It will be released. We
Yeah.
can release an alpha of this version by
Yeah, great progress, by the way.
Thank you. We can I appreciate that. We can release an alpha version of this version before the next month's call. We're now at monthly calls, by the way, if you remember. And we will also be working on the if you like sort of marketing or market preparation collaterals in terms of videos of usage to go along with that. So complete the tool, check the tool, debug, of course, and then alpha release, and then the development and release of videos walkthrough. So yeah, it's been a busy time, quite a bit of progress, quite a bit of work, and thanks to you all for your support and feedback. And so this time next month we should be done, and I'll send out a note once that alpha is available. All right. Any last questions before we close? Then if Eddie's back. Okay, great. Eddie, anything to add? I don't know if he's still. I see he's muted. He's probably still busy doing looking after things. Okay, let's close it there for this time. Thanks everybody for attending. Thank you for your insight and insightful comments, and we will look forward to hopefully more to show and tell next month around.
Thank you, Andy. Thank you.
Thanks for all the work, Andy. Thank you.
Cheers. Thank you very much.
Have a great day. Bye-bye.
You too. Bye.